and we're going to look at solving geometric problems now. The first part of solving geometric problems, this is fine from GCSE. Okay, this is something that is sort of from GCSE, but it is going to go a little bit more into A level on the next example that we do. So this one, I'm going to do most of this, but I want you to give me some help as we go along. Solving geometric problems. We've got a picture here of a parallelogram, and it says x is a point on AB such that AX to XB is 3 to 1. Boys. So it's already telling me that this ratio, AX to XB, from here to here is 3 to 1. Immediately, what I like to do in this is I like to say, well, this is the side that's got 3, this is the side that's got 1. It's just going to help me visualize what's happening. It then says that M is the midpoint of BC. So I might like to say, well, that's got to be a 1, and that's a 1. It's not necessarily saying that it is 1 long, but I'm saying this is a ratio of 3 to 1, this is a ratio of 1 to 1. It's half and half, okay? We could do it as a fraction if we want to. We can say this is 3/4, this is 1/4, this is 1/2, and this is 1/2. It's the equivalence there of fractions and ratios. As long as we've recognized that this is split into a 3/4 and a 1/4 because it's 3 to 1, and this is split into a half and a half. I think fractions actually, to me, and I think that's a good suggestion. We are now going to try and show that x to m, which is from here to here, is parallel to O to C, is parallel to this one. Now, when you look at them, although I've not necessarily drawn the line perfectly, they do look parallel. But it's quite an abstract thing. How can you prove on this shape that those two things are parallel if we didn't have vectors? It would be very, very difficult for us to do. But there's something that we know about vectors which helps us show when things are parallel. What did you just say? They are multiples of each other. Who said it? Was it red one? Zishan. So they are multiples of each other. So what we hope to show that that OC is some multiple of XM. I might just call it K, where K is a constant. I don't care if it's K, X, Y, A, B. The reason I didn't really use A and B is because I've already got like an A and a B in the question. So whatever, it's just some multiple of the other one. That's what we're hoping is going to happen in this question. So all I need to do is I need to find out what those values actually are. But I think before we get started, there may be some other things that are helpful for us to work out, because right now, the only things that we know which are vectors are OA and OB. Can anybody tell me any other vector pathway that you think might be useful for the question? Okay, we're definitely going to need to find out what O to C is. I think that's definitely going to be important. Anything else? And AB. I think we're also going to need to use AB at some point to try and do this, something to do with X, because X is on AB. So I'm going to start off and I'm going to find out what OC is. So to get from O to C, I go A plus B. This one is also a B over here because they're parallel to each other. It's a parallelogram. So OC is A plus B. I'm also going to try and work out the vector AB because I think that's going to be helpful. How do I go from A to B? Good. I'm going to go B minus A. And we're going to try and work out what the vector X to M is. Now we've got enough information, I actually think we can work out what the vector X to M is. So we're going to start at X, and we need to get to M. So how do I go from X to B? What can I say that the journey from X to B is? Good. It's a quarter of the journey from A to B, because that whole thing is A to B, and it's a quarter of that journey. And then how do I go from B to M? Good. It's a half of the journey from B to C. So that is a quarter. Now you can see why we worked out what AB is. A quarter B minus A plus a half. What is BC? Good. It's the same as O to A. So it's just A. So it's just a half A. And now I'm going to work out what this is. So we've got a quarter B minus a quarter A plus a half A. Just expanding the brackets there and writing those things down together. What will that simplify to? What does the A part simplify to? We've got minus a quarter plus a half. It's a quarter. Minus a quarter plus a half, or a half minus a quarter is a quarter. So I'm going to write that I've got a quarter A plus a quarter B. That is the vector from X to M. And then we go back to what Ishraq told us. It could be simplified. Yeah, it's going to be simplified. The thing that, I think it wasn't even Ishraq that told us, it was Zishan, sorry. We hope to show that this is true, that OC is a multiple of XM. This is OC. This is what we did all that hard work for, of finding out what XM is. Now we can just say OC is how many lots of XM? Is 4 lots of XM. Or we could have said a quarter OC is equal to XM. We can see that this is 1/4 of A, 1/4 of B, and this is A plus B, so it's a quarter of the whole thing. So we can say, so they are parallel. That's all you need to do to show that two things are parallel. You don't need to write an essay afterwards. You just need to say that this thing is true, and therefore they're parallel. Perhaps before that you could have said A plus B is equal to 4 lots of a quarter A plus a quarter B. You don't have to do that, because it's very clear that these two things are parallel to each other. More than just parallel, what can you tell me about the relationship between XM and OC? More than that they're just parallel. Good. OC is 4 times as long as XM. So if I wanted to write out the ratio OC to XM, it would be 4 to 1. Now, they haven't asked me this. This is some extra work that I'm doing. They haven't asked me this, but I just thought it's the kind of thing they might ask you. They might say, find the ratio of these two things. So you could do that and then find out how they compare to each other. It's kind of cool, actually, that you can, for any parallelogram, as long as these bits at the beginning are true, this will always be true. It's been shown, it's been proven properly. Just work through those steps again and think how we did this. Trying to show that they're multiples, found the pathways, compared them. We are going to do, the next example is the one that I think is a bit more tricky, okay? And then you're going to have a go at doing it, and then we're nearly at the end of vectors. Am I okay to go on the next page if people mostly got caught up with what I was writing there? Okay. This is where things, I think, get more interesting. Now, I'm going to tell you that I know that people usually find this difficult because I did this example again with my Year 13s. I'm teaching them Year 13 vectors right now, and they found this example. They were like, oh yeah, we didn't get this in Year 12. We found this really, really hard in Year 12. And I want to make sure that we absolutely nail this. This is an example that I would recommend you watching back again because it's challenging, but it's not too hard. No way is it too hard at all. Okay, let's break down what the question says. Let's first of all break down what the title says. It says introducing scalars and comparing coefficients. So scalars we've already come across. Those are the numbers that you can multiply a vector by to make it become longer or shorter. Okay, so that's fine. We know what introducing scalars mean. Comparing coefficients. What does the word coefficient mean when we talk about algebra? Yeah, the number before the variable, the number before the x. So if you had like 3x squared, the coefficient of x squared is 3. So we're going to compare the things that go in front of other things. So if we had an identity like ax squared plus 3x, and we said that that was equal to 2x squared plus bx, we can compare the coefficients to find out what a and b are. Very quickly, we can look at the x squared part, and we can just see that a has got to be equal to 2, because we're just comparing the x squared bits. When we look at the x parts, we can see that b must also be equal to 3, so that's all I've got written there. That's what we can do with algebra. We can do the exact same thing with non-parallel vectors. We don't have to just do it with normal vectors like a and 2a. We can also do it with other vectors as well. We can compare the parts of the vectors. That sounds a bit abstract. It won't feel as abstract when we actually start doing something in a second. Okay. We are going to read this question first, and then we're going to watch me do this, and then you're going to have a go. So it says OACB is a parallelogram. Notice the order of the letters, OACB. It goes OACB in that order. And it tells you that OA is A. This is the part I've said is the most important, so you should be listening. And OB is B. The diagonals OC and AB intersect at a point X. So the diagonals are crossing over at this point here. Prove that the diagonals bisect each other. There are some important words. Prove means you can't just say, oh yeah, well, like, look, it's just going to split in half, and I'll show you that it works when you split it in half. It means it needs to be much more sophisticated than that for it to be convincing. Bisect, I've kind of already said what that word bisect means. What does it mean to bisect? To cut it in half, okay? It means to be cut in half. Not cut in two, but to cut exactly in half. So we're hoping that this bit from here to here and this bit from here to here is half and half of that bit, and also that this bit here is half and half. But we're not going to be able to do that by presuming that it is. We have to presume that we don't know, and then show that it is a half. So maximum concentration, please, for this bit. I'm going to be using 2 new letters when I do some of these calculations. They're just letters that you'll come across, and I wanted to introduce you to them now. They are from the Greek alphabet, and the first one is called lambda, and it starts off like this. You start off by drawing that line, and then you add on a line underneath it. It looks like a Y that has been reflected upwards, okay? It's called lambda. It's the Greek letter that's round about where L is in the alphabet. So this is lambda. You do a curved bit and a line, a curved bit and a line, okay? You're going to be using this during the question. The second one is mu. Did we talk about this last lesson? Yeah. Okay, good. So why didn't you tell me? You were looking at me like... Okay, we've repeated it. It's good. Now we know what lambda and we know what mu is. And mu is, we use mu quite a lot, okay? I suddenly, as I was saying it, I was like, I'm sure I've said this to you guys. Anyway, we are going to try and find out what OX is in 2 different ways. This is the strategy of this question. We're going to try and go from the origin to this point here in 2 different ways. Well, one of the ways to go from O to X is that I could journey some fraction along the way of OC. Now, we want it to be a half, but we can't say to get to X it's halfway because we don't know that it bisects. We're trying to prove that it bisects. So I'm going to say OX is some fraction of OC. And I'm going to say here where lambda is going to be between 0 and 1. In other words, it's a fraction. We know that the answer is lambda is a half, but I cannot say that lambda is a half because I'm trying to prove that it is a half, okay? That's one of my ways that I can go from O to X. I can go from here some fraction of the way along there. Can somebody describe a different journey that I could take to get to X? Oh, what letters could I use that could take me from O to X, but without going along that blue line? I could go from O to B and then... Yeah? Yeah, I could actually just go from O to B, and then I could go from B to X, okay? So OX is going to be OB, which is B, plus, I don't know how far along this bit I'm going. I don't know how far along this BA that I'm going to take a journey of, plus some fraction of BA. I'm not going to go all the way along BA. I'm only going to go some way along. We know how far we're going. We know it's going to be a half. But again, we can't actually say that it's a half. So actually, I better quickly work out, what is BA? How do I go from B to A? Minus B plus A, or A minus B. Oh, look, we've got that same pattern, BA, A minus B. Same thing that we had in the first half of the lesson. So coming back to the red part now, I can take this and I can put it in here. So OX is equal to B plus mu lots of A minus B. I'm going to keep working on this OX, and I've got B plus mu A minus mu B. Good, you're concentrating really well on this. Keep it going. I'm going to keep manipulating this a couple of stages more. So I have mu A plus B minus mu B. I've just rewritten the order there. Bless you. And what shall I do with these B vectors at the end? Good, factorize them. So I'm going to do my final line that I've got written here. I've got mu A plus, when I factorize this, how many lots will it be in the bracket? I'll have B multiplied by 1 minus mu. Okay, let's just pause for a second and take stock of what we've done. Because we're trying to prove that the diagonals bisect each other, we had to journey along both of the diagonals for that to make any kind of sense. We couldn't just do it going along one of the diagonals, because that's not proving anything. It needs to involve both of the diagonals if we're going to prove that they bisect each other. So what we do is we come up with the journey OX in two different ways. One of the ways that we've come up with is this very, very simple one. Another way that we do this is all the way down here, which is a bit more complicated. I perhaps should have mentioned here, where mu is also between 0 and 1, where it's a fraction. We're just saying you're not going all the way along BA, you're just going some of the way along it. It won't be equal to 0 or 1. There's no way it's going to, we know it's a half, but I'm just trying to say to you it's a proportion. It's some distance along that journey. We don't know how far along it is. We can tell with our eyes it's halfway, but we're trying to prove something that would be permanently true. Once we've come up with these two statements of these two things that we've got here and here, in fact, I'm going to do a little bit more work on this blue one. I've realised we didn't quite finish that off. This blue one, we should have also said that OX, I don't think I can fit that in. Let's take it down here. We've also got the OX from the blue one is lambda lots of, what is the vector from O to C? B plus A, yeah, it's A plus B. I should have said that before, sorry. It is A plus B. So we have lambda A plus lambda B. This is what OX is equal to. So the two things that I'm actually most interested in is this one and this one that I've got down here. I'll move it down so that if you can't see the bottom of the board, you can now see it a bit more easily. We are now at the stage where we've introduced the scalars. What did the title say was the next thing we needed to do? We're going to compare the coefficients. So I'm now going to compare this coefficient, which is the A part, with this part. When I compare those two things together, what does that tell me about mu and lambda? They have to be equal to each other. Mu has to be equal to lambda if OX is going to be true for both of these things that I've got here. The next thing that I know is that the B part, 1 minus mu and lambda b, they have to be equal to each other. So I get 1 minus mu has got to be equal to lambda. This came from the A part. This came from the B part. I've now got simultaneous equations. So I'm going to take this second equation here, and I'm going to replace this lambda with mu, because I'm going to solve these two equations simultaneously. This gives me 1 equals 2 mu. Mu is equal to a half. Now, if mu is equal to a half, we know that mu is equal to lambda. So we also know that lambda is equal to a half, which is great, because that's the thing we already knew at the beginning, but we were trying to prove this. And proving this is not as simple as just saying it works. This is way more sophisticated now. This just requires a final thing. So the diagonals bisect. If you got that mu was a different value, if it was like 2/3, then we would know something about how far along that line it intersected. It wouldn't be half and half. I think it's a challenging question because if you look at the page, there are no numbers until over here, where you get the number 1. And then you get no more numbers until you get another 1, and you get a 2, and then a half. This is a question that is, I think, really cool, that the whole of this scenario is described using journeys, and we can make a proof about those journeys. I'm going to leave this one up on the board here, and then if you've got any questions, you can ask me those questions. But you've got one to try that's on the next page, okay? So I'm just going to pause my video here.